Okay, last time we were starting to talk about turbulent flow, and we got as far as basically saying the turbulent flow can be described as some mean velocity in this turbulent region, that some mean velocity combined with some random oscillation of velocity around that mean. The transition to turbulence happens at this critical Reynolds number. So the critical Reynolds number is basically when the inertial forces of the flow outweigh the viscous forces that are damping the inertia. So at this critical Reynolds number, which is roughly 5e to the fifth for most external flows, you start getting instability and it becomes a turbulent flow. So now let's talk a little bit more in detail about what the turbulent boundary layer looks like. Laminar boundary layer is this nice kind of growing wave that propagates away from the surface. In turbulent flow, that's kind of different, and so some different things govern the behavior in that region. So let's get into that discussion. Okay, so for the turbulent boundary layer, let me kind of give you some indications of what's happening as far as like the anatomy of this boundary layer. So again, we have, let's say we're starting off with flow from this free stream. It comes into contact with a plate. The boundary layer, remember, is the region of fluid that's affected by the presence of the plate. So if we're just talking about momentum or velocity considerations as we are now, then we're only looking at the part of the fluid where the velocity is affected. So the laminar grows as you would expect like this. And then let's say at some position, let's call this position here x critical. At x critical, the Reynolds number exceeds the critical Reynolds number, and we start transitioning to turbulence. First thing I'll say is it's never like a clean, immediate transition, right? There's this kind of gradual transition region where you start seeing instabilities, and then it's not really full-fledged turbulence until further down the road, at which point you really start getting this full eddy effect. The only time when you have a real clear transition from laminar to turbulent flow is usually if you purposely trip the flow. So in that video I showed last time, they had at the front of the plate, they had a wire, and that wire disrupted the boundary layer and forced some kind of turbulent behavior to take place. That's normally the only real clean transition you're going to see. So for now, we're going to draw it as if it's like a sudden transition, but just keep in mind that there's usually a transition region. Okay, so this transition happens. All of a sudden, the boundary layer starts to grow, but it grows kind of randomly, right? This kind of chaotic, random growth. That's the entire region that's affected by this. But one other thing that's happening here is you actually get this very small region right next to the plate where the shear forces of, or the shear in the fluid, the forces are strong enough to still maintain laminar flow. So you get this like these big eddies that form, but this little sublayer called a viscous sublayer forms. So right at this transition, you start seeing this viscous sublayer comes down here, and it starts to form as well. Right, so kind of right next to the plate. It's more stable than I drew it, right? It's kind of like a nice flat line. And this little region is the region where, like I said, all the shear is happening. All that velocity gradient is basically happening right next to the wall. And so you have enough shear force where it's overcoming the momentum and keeping things laminar. So let's just kind of label some of this stuff. So here we have delta, oops, sorry. Here we have delta M laminar, that's this boundary layer here. Here we have this distance here, let's call this delta M turbulent. This is the overall turbulent boundary layer thickness. And then down here you have the viscous sublayer. Let's call this delta VS. All right, so as I sort of mentioned, the important features here are that within the turbulent boundary layer outside of the viscous sublayer, things are kind of chaotic. There's a lot of transport happening. There's a lot of movement away and towards the plate. But on average, the gradients in velocity and the gradients in temperature are really pretty small, right? And if you think about it, it sort of makes sense because let's say you're out here, you're some particle out here. It's very easy for you to move in this direction because of the bulk transport from these eddies. So because it's really easy to move, it's almost like saying the effective conductivity or the effective viscosity is really high. And if that's the case, then the gradients are going to be low, right? The temperature or the velocity gradients are going to be really low. So, okay, so then if that's the case, all the action's happening right next to the wall. All of the gradients happening right in here in this viscous sublayer. So let's maybe put some concepts to this, and then you can kind of see how we're going to end up modeling it. So if we're thinking about this in terms of temperature, right? Let's say you have a surface temperature, maybe here. Let's just call this Ts, and out here we have some T infinity. If I'm thinking about heat transfer and developing a model of heat transfer, I basically have like two resistances that I'm worried about. So the first resistance would be from the surface here across the viscous sublayer. And then the second resistance would be from the viscous sublayer boundary out to the edge of the turbulent boundary layer. So these two resistances are both things in series that have to be overcome for heat to move from the surface out to the free stream. So let's just maybe put some values here. So this viscous sublayer, the resistance is basically going to be delta Vs over K, right? That's the fluid conductivity. And why is that? Well, it's the distance to K. And the fluid conductivity here is the actual, like, you know, thermophysical property of conductivity, as opposed to like an effective conductivity that you'd see out in the turbulent region. So let me just kind of put that down. So out here we have delta T turbulent. Right, before I say delta M, but delta T. This is the thermal boundary layer. So we're modeling temperature here over conductivity. But this is K turbulent. Okay, so just to make sure you're clear on what I'm saying here with these two different conductivities. So we have a boundary layer. The boundary layer consists of the overall thickness and the viscous sublayer. In the viscous sublayer, it's still laminar flow. So the mechanism of heat transfer is conduction. So that mechanism is governed by K, the fluid's conductivity. In the turbulent region, where you have all these eddies, it's not just conduction that's occurring. It's conduction and advection, right? You have this fluid, and it's sort of circulating around. So there's an effective transport, effective conductivity called K turbulent. K turbulent is going to be much, much higher than regular K. So let's maybe note that. So K turbulent, the effective conductivity is much higher than the fluid's inherent conductivity. Same thing is true by the way of viscosity. So if we were doing this for momentum, it'd be mu turbulent is much, much higher than mu. But when it comes to like the thicknesses of these different layers, we'll note that the viscous sublayer delta Vs is much smaller than the laminar boundary layer, which you can see here, which is in turn much smaller than the turbulent boundary layer. Right. Viscous sublayer is smaller than the laminar, which is smaller than the turbulent. So all these things kind of have to combine together to get some combined estimate of the heat transfer that's occurring. So let's say we're going to estimate heat transfer. Let's do this with a resistance model. So we would say the convection resistance is equal to the resistance of the viscous sublayer plus the resistance of the remainder, right? We'll call that the turbulent layer, which is now, as we've said, equal to delta Vs over K plus delta T turbulent over K turbulent. So what do we do with this? Like what we're trying to do is figure out say, heat transfer rate or something like this based on the resistance. So we have delta Vs over K. As long as I have a model for the viscous sublayer, I can estimate the thickness of the viscous sublayer. I can look up conductivity, and I'm good, right? On the second term, it turns out that in most cases, this is negligible. And why is it negligible? Well, delta T, this turbulent boundary layer, that's a pretty high value. Right, so I drew a 1 arrow there. It's a pretty high value. K turbulent is a very, very high value. So let's draw 3 arrows. Right, so a pretty high value divided by a very, very, very high value is 0. So normally this term here is basically goes to 0. So that's great because it helps us be able to model turbulent flow by basically not caring what's happening in the turbulent region except for in the viscous sublayer. So as long as we have a good model of the viscous sublayer thickness, we can effectively model the heat transfer in a turbulent flow. We don't care about all this chaotic stuff. It doesn't really affect anything as long as we know what's happening in the viscous sublayer. So if we actually write all this out, we would say our model is then Q dot double prime in the turbulent region is equal to the surface temperature minus the free stream temperature divided by the viscous sublayer, K over viscous sublayer. Right, so this is our approximate, should do this approximate. This is our approximate model. Turbulent heat transfer rate is equal approximately K over Vs, it's our resistance, times the temperature potential. Okay, so this hopefully gives you kind of an understanding of what's happening when we're talking about heat transfer in a turbulent problem. Again, everything comes down to the viscous sublayer and thinking about the mechanisms there. There are models where you're going to want to, more advanced problems where you're going to want to estimate things like the conductivity in the turbulent region, K turbulent, estimate the boundary layer thickness, and so on. For this class, we're going to kind of limit it to this type of problem and talk really only about the viscous sublayer. So on the homework, I think you have, I give you, for example, a model of the viscous sublayer thickness for a turbulent flow over a flat plate. You would use that model then to estimate the heat transfer rate or temperature or whatever it might be. Okay.